All right, let's peel back the layers on a fascinating puzzle in the world of artificial intelligence. We often hear about how advanced AI is becoming, especially with understanding language and complex reasoning. But what if I told you that when it comes to simply seeing the world, like you and I do, the most sophisticated AI models, these incredibly powerful multimodal large language models, or MLLMs, are still spectacularly missing the mark? It's like they've mastered the grammar of thought, but haven't quite learned the poetry of perception.
What's truly intriguing here is that while MLLMs have made incredible strides in tasks involving knowledge and abstract reasoning, a fundamental question persists. Can they truly perceive the world as humans do? This deep dive is all about a new benchmark called the Turing Eye Test, or TET, which focuses precisely on that question. What makes human visual perception so effortlessly poetic compared to AI's often literal interpretation of pixels?
So our mission today is to dive into this groundbreaking paper aptly titled Pixels, Patterns, but No Poetry, and extract the key insights for you. You'll discover why even state-of-the-art MLLMs exhibit what the researchers bluntly called catastrophic failures on visual tasks that are utterly trivial for us. It's like a scientific mystery, really, and we're going to piece together the clues. Okay, so for years, benchmarks like MMMU, MathVista, and MathVision have shown MLLMs excelling in complex visual reasoning tasks. These models can handle intricate problems when the visual input primarily serves as a prompt for their reasoning abilities. But here's the crucial distinction, right? Those benchmarks primarily test the language backbone. That's the reasoning part of the AI, the brain, if you will. The Turing Eye Test shifts its focus entirely to perception. It asks, can they really see? Not just reason about what's in a picture, but genuinely interpret the visual information in a human-like way, discerning patterns and meaning that aren't explicitly spelled out.
Exactly. The TA is comprised of 4 unique diagnostic tasks, each meticulously designed to challenge the vision tower of these models in ways humans process intuitively. And just for clarity, when we refer to the vision tower, we mean the part of the AI that crunches all the visual data, like image recognition. Essentially, it's eyes. Each task exposes a different facet of what MLLMs struggle with, highlighting their inability to handle visual information beyond a very literal interpretation.
All right, so our first challenge for the AI was called hidden text. Imagine an image where a word or phrase is subtly formed by the arrangement of objects in the scene itself. When you see it, the word just pops out at you. It's seamlessly integrated into a larger image. The text is rendered as shapes within the figure, appearing as clear text when the image is reduced in size, but resulting into a complete, more detailed image when magnified. It's a cool trick designers sometimes use, but I guess it's intended to trip up the AI here.
That's the idea. This tests holistic pattern recognition, the ability to see the forest and the trees, so to speak. Humans immediately grasp the macroscopic symbol, processing both the details and the overall composition simultaneously. What they found to be remarkable here is that MLLMs consistently fail to perceive these overall symbols. For instance, in one example provided in the research, a model completely missed the word star hidden in the scene. Instead, it focused on a circular object on a building and misidentified it as the letter O. It's like they're reading individual pixels or tiny elements but can't see the word itself. It indicates a fundamental lack of global perspective when processing such images. The AI is just lost in the granular details.
So it's not just that they miss the word, they actively misinterpret parts of it, like that O example. It's like their focus is too narrow. That brings us to our next challenge, 3D CAPTCHA. Think of those distorted, curved characters in a three-dimensional space, the kind you sometimes see to prove you're not a robot online. They are rendered as alphanumeric sequences, intentionally challenging even human vision sometimes, but for good reason.
Right. This task specifically evaluates 3D spatial character recognition, a task humans complete almost instantly, even if it takes a second look sometimes. For MLLMs, well, it's pretty much a non-starter. They often interpret these images as generic graphical representations, like waveforms or 3D plots. They fail to see any characters at all, even when the ground truth might be something like DQQ5N. The particular composition patterns of these characters make the models prone to significant interference. They just can't seem to discern the intended characters from the visual noise.
Okay, it's clear they struggle with these spatial distortions. But what if the challenge isn't just about perceiving individual characters? What about understanding meaning woven into complex visual forms, especially in another language?
Yeah.
That's where Chinese ligatures came in. These are complex Chinese character compositions, synthesized through decomposition, morphological transformation, and fusion of multiple characters to form a single, meaningful glyph. Often they represent a complete idiom or proverb, like the phrase for marital bliss, encapsulating a deep cultural meaning in a single visual unit.
And this task truly challenges both decomposition and recognition of complex character structures, along with the ability to infer broader meaning. MLLMs can sometimes perceive individual components within these ligatures, but they fundamentally lack the imaginative capacity to extend those components into commonly used sentences or holistic concepts. They engage in a rigid recognition of obscure individual characters, completely missing the broader idiomatic meaning, such as the full idiom for marital bliss. They just can't make that cognitive leap that a human would.
And finally, our fourth test was colorblind charts. These are similar to the Ishihara charts used to test for human color blindness, right? Where characters are formed by dots against a background of confusing, chromatically similar dots. These images were specifically augmented with confounding dots to increase the recognition difficulty for a machine, making the underlying character a truly subtle pattern.
Exactly. This assesses pattern perception within dot matrix arrangements. Humans can mentally construct the character from the overall shape formed by the similarly colored dots, despite the visual noise. We just sort of piece it together. MLLMs, however, are easily disturbed by the surrounding circles of the same color. This leads to frequent recognition errors, sometimes identifying EUC instead of the actual character M3, for example. They struggle to piece together the character from the subtle color differences in the overall shape. The noise just overwhelms their ability to find the signal.
Okay, here's where it gets really interesting and frankly quite revealing. Across all four of these domains, hidden text, 3D CAPTCHA, colorblind, and Chinese ligatures, the performance of state-of-the-art MLLMs was consistently and substantially below acceptable thresholds. And this includes models like OpenAI O1, Class 4 Sonnet, Gemini 2.5 Pro, and many others. We're talking the best of the best here. Many models achieve 0 success rates on the first attempt, which we call passive 1-0. This means they couldn't even get it right once. Even when given 32 attempts, what we call passive 32, the improvements were marginal, often still near 0%, with peak performance gains remaining below 4%. I mean, truly abysmal results across the board. It begs the question, why this profound failure?
That's the million-dollar question, isn't it? Why are these models failing so spectacularly on tasks that are so intuitive for humans? Researchers employed a technique called GradCam to visualize what the models were looking at. It's essentially a heat map showing where the AI is paying attention in an image. They found that models typically fail to correctly locate the target regions. It's an attention problem. This applies both to their visual component, the vision tower, and their reasoning component, the language backbone. The vision encoder often struggles to focus on the textural features that make up characters, instead prioritizing object-level features, like seeing the individual dots but not the letter they form. Similarly, the language backbone scatters its attention over irrelevant regions or completely ignores critical visual elements. The AI literally isn't looking at the right thing.
That's fascinating to think about the AI having, technically, perfect vision, but constantly looking in the wrong direction. So the eyes might be technically capable, but the attention is flawed. It's not just about what they see then, but how they learn and adapt. The researchers explored if giving the models more context, perhaps through in-context learning or fine-tuning their language abilities, would help them bridge this perception gap.
They did. And connecting this to the bigger picture, the findings were quite clear. Methods like in-context learning, where you provide examples during inference, or fine-tuning the language backbone, the reasoning part provided virtually no improvement. For example, incorporating domain-specific data as examples during inference yielded almost no gain in performance. This really indicates the problem isn't a lack of knowledge or pure reasoning ability. The truly fascinating part, the key finding really, is that fine-tuning the vision tower, the part of the model that processes images, enabled rapid and significant adaptation. For example, on the colorblind task, accuracy shot up to an astounding 99.33% with visual fine-tuning. Yeah, compared to almost 0% before. It's almost like giving the AI a pair of glasses after it's been stumbling around blindly. This strongly suggests the bottleneck lies squarely in the vision tower's generalization abilities and its fundamental visual perception capabilities, not its language knowledge or reasoning.
Wow, 99.33% from near zero. That's a massive jump. So if I'm understanding this right, it means the problem isn't with the AI's brain, its language and reasoning, but specifically with its eyes not knowing what to focus on or how to interpret what it sees. Another intriguing experiment involved how changing image resolution affected performance on the hidden text task, didn't it? Offering more clues about how these vision models truly process images.
Indeed. When images were directly downsampled, model performance actually improved as the downsample factor increased.
Improve, that seems counterintuitive.
It does at first glance. But it's because downsampling simplifies the image content within each fixed-size processing patch the vision model uses. It effectively highlights the character textures. At extremely low resolutions, the original image basically degrades into simpler character patterns, making the task more akin to standard optical character recognition, which models are already pretty good at. However, when images were just blurred without resizing, performance degraded.
Okay, that makes more sense.
Right, because blurring introduced additional noise and made character textures ambiguous within those patches. This directly aligns with how vision encoders process images by partitioning them into fixed-size patches. It reveals their sensitivity to subtle image content within those defined areas. They need clarity within their processing window.
So what does this all mean for you, our listener? What's the bottom line here? This deep dive into the Turing Eye Test clearly shows that despite incredible advancements in AI reasoning, there's still a significant fundamental gap. A gap in how multimodal large language models perceive the world compared to us. Our intuitive ability to see patterns, understand 3D space, extract meaning from noise, and creatively interpret complex visual compositions remains a distinctive human advantage. It's a frontier that current AI struggles to cross. It's the poetry that AI is still striving to learn, isn't it?
It really is. And this raises an important question for the future of AI development. The research suggests that to bridge this perception gap, the next frontier might involve integrating reasoning capabilities not just after perception, but into the perception stage itself. Imagine training the visual component of AI to reason about what it's seeing, rather than just passively processing pixels and then sending them off to a separate language module for interpretation. It's a paradigm shift from see then think to think while seeing, potentially, and that could finally unlock genuine human-like understanding. What possibilities might that unlock for machines to truly see the world, not just analyze it?